Hello, viewers. It was okay. Gonna wait a little bit longer for more people to join the live stream. Wait about one more minute. All right, looks like no one else is joining, so I'm gonna start. Um, okay, so we are moving on from kinematics. Kinematics is all about describing motion. How do we describe motion? And we describe motion in terms of position, velocity, acceleration. But we haven't talked about what causes motion. So today we're going to start to talk about that. This lesson should be mostly review, except there are some of you in this class who did not take AP Physics with me, AP Physics 1 with me, so this will be new for you. But for everyone else, it should be more or less review. And I kind of meant for it to be a breather because I know that the last quiz that I assigned was pretty challenging. So, all right. So what causes motion? Motion is caused by things called forces. And a force is basically a push or a pull. With a certain strength and a certain direction. Okay, so strength is another word of saying magnitude. So basically a force is a thing that has a magnitude and a direction. So it is a vector. Okay, vectors are things with magnitudes and directions. We will denote forces by F, and the units of force, which I indicate by putting square brackets around it, are newtons, which we will abbreviate as N. Okay? There's a thing called the net force, which is equal to the sum, the vector sum, of all the individual forces that are acting on an object, and there could be lots of them. That's called the net force. Forces are 2 or 3 dimensional. So let's do some examples for how to manipulate forces. So let's suppose an object experiences a 30 Newton force in a direction 25 degrees west of south. And a 60 Newton force, this should say force here, pointed let's say 40 degrees north of west. What is the magnitude of the net force. Okay, so I haven't explained what this means. The 25 degrees west of south, 40 degrees north of west. So what we want to do is let's draw our cardinal directions, all right? So we got north, south, east, and west. So the 30 Newton force points in a direction 25 degrees west of south. So I'm going to start off with south, and then I'm going to rotate in the western direction 25 degrees west. Okay, so west is leftward, so I'm going to rotate 25 degrees leftward from the southern direction. So that might be a direction that's kind of like this, I guess. All right. So that angle right there is 25 degrees, and this is a 30 Newton force. Okay, I know that's a little tough to read. I'm going to draw it bigger over here in a second. And then we have a 60 Newton force pointed 40 degrees north of west. So I'm going to start with the westward direction, and then 45 degrees is kind of halfway between west and north. So I go 40 degrees north of west, so a little bit less than that, then halfway between north and west. And I want to draw this vector as being twice as long because it has twice the magnitude. Okay, so I tried to make this arrow twice as long as that arrow, and this would be 40 degrees. If it was 40 degrees south of west, it would be pointed down in this direction. So how could we find the net force? Well, I taught you back in the very first lesson that had content that the net force, or to add vectors, you use the parallelogram method. So I could create a parallelogram out of these two forces. Boom, like that. That is the net force. And so by asking for the magnitude of the net force, I'm essentially asking for you to do the Pythagorean theorem on this vector. Okay? So this is how you would do this problem in pictures. It would be the length of that arrow would be the answer. But if we're trying to do this algebraically, we need to get both of these vectors in ij form. Okay? So let's start off with the first force, which is 30 newtons, and it has a direction 25 degrees west of south. So what I want to do is I want to get the components, the vertical component and the horizontal component, which would just be the legs of this right triangle, okay? So to get the vertical component, I notice that the vertical component is adjacent to the angle, so I'm going to use cosine because cosine is the trig function with adjacent in it, adjacent over hypotenuse. So this is going to be 30 cosine of 25 degrees. You want to make sure your calculator is in degree mode. And then this leg of the triangle is opposite the angle, so that's going to be sine, 30 sine of 25 degrees. So I'm going to plug these into my calculator really quickly. 30 cosine of 25 is about 27 newtons. I'm going to round these to just whole numbers. 30 sine of 25 is about 13 newtons. So if I call this vector F1, I can see that this vector goes to the left and it goes down, so that means it has a negative I component and a negative j component. So this is actually the vector minus 13 I hat minus 27 j hat. And I'll put parentheses newtons afterwards to indicate that I'm measuring those in newtons. Okay? Let's do the same thing with the 60 Newton force. 60 Newton force looks like this, where this is 60 newtons. And then this is 40 degrees. That doesn't look like 40 degrees. I messed up this drawing. So to get the vertical component is opposite the angle. So that means I'm going to use sine. Sine is opposite over hypotenuse. So this is going to be 60 sine of 40 degrees. And the horizontal leg of the triangle is adjacent to the angle. So this is going to be 60 cosine of 40 degrees. So this one is about 39 newtons, and this one is about about 46 newtons. So if I look at force 2 goes up and to the left. So it's going to have a negative I component to indicate that it's going to the left. And it's going to have a positive J component to indicate that it's going upward. So plus 39J, parentheses newtons. Okay, so if I want the net force, I need to do the vector sum of those two. Okay, so if I do the vector sum, that's going to give me the net force. And to add together vectors, I do I component plus I component, J component plus J component. So negative 13 plus negative 46 is negative 59. 39 plus negative 27 is 12. So we can see that this vector goes to the left a lot and it goes up a little bit. So that is pretty consistent with our drawing, right? It goes to the left a lot and it goes up a little bit. So that gives us confidence in our answer as being correct. So now if we want the magnitude of the net force, we would go do the magnitude. And magnitude means do the Pythagorean theorem on the resulting vector. So I'm going to do the Pythagorean theorem. Square root of 59 squared plus 12 squared. The minus sign gets squared away. So I plug this into my calculator here. And I get about 60 newtons. So that's our answer. The magnitude of the net force in this case is about 60 newtons. One thing I want to point out to you is that the answer is not 90. Okay? The magnitude of the net force is not equal to the magnitude of the first force plus the magnitude of the second force. This is not true. No. Okay? I answered this problem probably 4 or 5 times since the class has begun, where people were taking the magnitudes first and then adding or subtracting the magnitudes. But really what they should have been doing is adding them or subtracting them as vectors and then taking the magnitude. So almost all the time, when you want to get the magnitude of a sum or a difference, you need to add as vectors first and then do the magnitude as the very last step. Okay? So that is a mistake that I've seen several times since we've started the school year. All right. So now I hope you feel comfortable dealing with forces mathematically. So now let's So that really has nothing to do with physics, what we just talked about. We just kind of were doing vector addition. Now, let's talk about Newton's laws of motion. And there are 3 of them. And these are just observations about how the universe works. Answers always need to be within 2%. Okay, so Newton's first law says that objects in motion stay in motion and objects at rest stay at rest whenever there is no net force. Okay, so basically what the first law of motion is saying is that a net force is a thing that changes the state of motion. Okay, so I like to think about sort of the converse of Newton's laws of motion. So what would be the converse of Newton's first law of motion? It would be objects in motion do not stay in motion. Objects at rest do not stay at rest. So that would mean things sort of just that are moving just kind of can stop moving spontaneously, or things that aren't moving can start moving spontaneously. So really what we are getting is basically that if you want to change the motion, you have to have a cause for it. There has to be a reason to change the motion, and the net force is that reason. If I was going to state this first law of motion in as concise of a manner as possible, I would say that if the net force equals 0, then the velocity is constant. Okay, so this is the most concise mathematical way of stating Newton's first law of motion. The second law of motion is an equation. Okay, it says that the net force on an object is equal to mass times acceleration. Okay, so this is the acceleration vector. And this is the mass. Mass is, of course, a measure of the amount of stuff. Okay. It is a scalar. Scalar, remember, is a something that has no direction. It's pure magnitude, no direction. So in other words, you would never say that I have a mass of 50 kilograms northward. That makes no sense because your mass has no direction. Notice that we have a mass, which is a scalar, multiplied by acceleration, which is a vector. So Newton's second law of motion is really a scalar multiplication. Okay, so this is, once again, this is going to be the most important equation in this course as well as the previous course. Okay, really, I like to think about Newton's second law and Newton's first law as statements of cause and effect. Okay, the effect is change in velocity. Which is another way of saying acceleration is happening. All right. and the cause is a net force. You can't have change in velocity without a net force. So there's cause and effect. The third law of motion has to do with the interaction of two bodies, okay? It says that for every action, there is an equal and opposite reaction. Okay? So let's say that two things, here I have object A and object B. And here is the force that B exerts on A. Then the force that A exerts on B is going to point in the opposite direction, so that's the opposite part, and it's equal in the sense that both of these forces have the same size. They're the same magnitude forces. So that would be the force of A on B. Okay. So kind of the super concise mathematical way of saying Newton's third law is to say that the force of A on B is equal to minus the force that B exerts on A. All right? So that is the statement of Newton's third law. So let's try and delve into what is the third law saying. Well, again, I like to think about the converse. What if the force that A exerts on B is not equal and opposite to the force that B exerts on A? So let's consider what if you were to punch yourself in the face, all right? And I talked about this last year, but maybe you forgot. If you punch yourself in the face, so here's your face, punch yourself in the face. There is a certain force that your fist exerts on your face. Okay? And let's say that that force has a magnitude of 80 newtons. What if the reaction force was not equal? What if the force was unequal but opposite? In that case, the force that your face exerts on your fist, okay, might be less than 80 newtons. Maybe it's only 30 newtons. In which case, because these are opposite, but they're not equal, they don't cancel each other out. And so the size of the net force would be 80 minus 30, which would be 50 newtons. So that would mean that by punching yourself in the face, you could exert a net force on yourself. And if there's a net force on yourself, according to Newton's second law, you would accelerate. So you could actually punch yourself in the face and accelerate into the air if you wanted to. We could all fly if Newton's third law was not true. We could all fly by just punching ourselves in the face repeatedly, and then we would accelerate into the air and we could punch ourselves to our destination. All right? Unfortunately, this is not true. All right? So basically what Newton's third law is saying is that in order to accelerate, one must push off something else. If you want to walk, you need to push off the ground. If you want to jump, you need to push off the ground. Now this gets really tricky when you're in outer space. So how do we move around in outer space? How do we change our velocity in outer space? Because in outer space, there's nothing to push off of. So the solution to that problem is, if you're in outer space, is we bring extra stuff with us called reaction mass, and we push off of the reaction mass to change our velocity. Now, the reaction mass, if you're in a rocket, is of course the exhaust. Okay? So a rocket pushes off of its exhaust in order to accelerate and change its velocity. Now, the bummer is that once you run out of reaction mass, once you run out of fuel, you can no longer accelerate and your velocity will just remain constant. So you want to make sure that you have enough reaction mass before you try to go into space, all right? Otherwise, you're going to be in a lot of trouble. So, there's a lot of planning that goes into to space flight, okay? Because you got to make sure you have enough reaction mass. Another sort of goofy thing we could have is, what if for every action there was an equal reaction, but not an opposite reaction? Okay, what if it was equal but perpendicular? All right, so that would be something like, you apply a force on the calculator, but it doesn't accelerate in the direction you expect it's going to accelerate. So you push something and then it accelerates down. So you could it would just be really annoying. You would just push on something and it would go to the side, and you push and it would go to the side, and you push and it would go to the side. It would just be weird. Okay. So in order to accelerate, you have to push off something else. Oh, one thing we could talk about is jets. How is a jet different from a rocket? Well, a rocket can operate in outer space with nothing else around it. A rocket works. However, a jet does not bring any reaction mass. A jet pushes off the air itself. So a jet, so the thing that gets pushed off of, the jet does not work in a vacuum. The thing that the jet is pushing off of is it's sucking in air from the atmosphere and pushing off of the air. All right, so if you have so you don't need reaction mass in a jet, which is why flying in an airplane is so much more simple or in some respects is more simple than flying through space. In other respects, flying in a jet is a lot more complicated because the forces are so much more complex from the atmosphere. In outer space, there aren't any complicating forces. The forces involved are much more simple. All right, so that's my lesson for today, and let's go ahead and switch over to the Zoom room.